Okay, so as Farang said, I will talk about the discrete element method today from a practical point of view. Okay. The idea is to approach the physics of granular materials with the discrete element method. So by considering a collection of elements, of rigid elements, rather than a continuum. During this introduction, I will show you some piece of code. They are small part of codes that are written in JavaScript. But actually, we do not matter about the fact that it is written in JavaScript. It is just because with this language, I can display things and it's easy. Normally, the DEM code, the one you will use or you will develop, is written in a language which is like C, C++, Fortran, something like this. So here the objective is only to build a deeper understanding of the DEM, not to make a code. If you are looking around you, you will see that I would say the granular materials are omnipresent. But I would say that everything actually is granular. It is a kind of joke, but everything is granular. We can start from the atom size that are discrete elements. Others, you can go to gravel, spheres, and up to planets if you want. The only difference is the interactions between the elements that are different, but everything is granular. So you can use them all the time. But actually, it is not really the case because sometimes it is more efficient to consider the material as a continuum. So here we will see what is a classical usage of the DEM. The DEM is a discrete element method, as you know. And why we do that? Because in discrete element method, as already said by Farang and Jean-Noël in the previous talk, there are numbers of very striking properties, things that appears to be strange, but actually when we model them with the DEM, we can reproduce them. So here are some examples of striking properties. In this example, we write some grains, chickpeas, with weighting matching, and we find this weight. Then we try to do the same, but this time we use a tube, which is fixed. And below the tube, we've got the weighting machine, but without contact anywhere. There's no contact. We put this quantity of grains inside the tube, and the weight becomes that. So it appears to be strange, but actually it's very easy to understand. It's only due to the fact that each grain can, we have friction between the wall of the tube and the grains. And if we did the same with water, for example, without making sure that the water cannot go through, we should have the same weight. But with a granular material which flow like water, we don't have the same weight. So this is an example. Another example is concern the volume. If you took half a liter of small particles with half particles with a little bigger particles, we would expect to have 1 liter as a result, but actually we've got less. With liquid, this is not the case. But with granular materials, the fact that the small particles can go in between the voids between the big particles result in the volume which is less. So the explanation one more time is it's easy to understand, but this is a particular property of granular materials. It's less evident if we cannot see the particles. one more example. If we take, maybe you know this experiment. If we take sand inside a plastic bottle with on the top a tube, and everything is saturated with blue liquid, okay? We press the bottle, and we would expect that the liquid rises, but actually it goes down. So it's strange, but it's simply due to the fact that we've got particles. And when we shear particles, the void in between the particles will increase. So the liquid will come inside. So the explanation is not necessarily complicated, but the resulting behavior at the macro scale appears to be strange. Okay, fourth example, which is the segregation. When we've got different kind of particles in terms of shape, the surface aspect ratio, the weight, something, they will segregate. And we will observe some things like this in the nature. And one more time, with DEM modeling, we can assess, we can model easily this kind of feature. Okay. Personally, when I use DEM, I use it to model granular matter that are soils most of the time. So typically, what we will try to assess when we load a granular matter, a soil, is the mean pressure. So the mean pressure is defined as the 1/3 of the stress, the total stress. Huh? And the second thing is the deviatoric stress, which is defined like this. But we may illustrate it like this. If we consider the three components of stress, the main stress, the pressure is along the hydrostatic axis. The deviatoric plane is normal to this axis, and the distance of the current stress state with this line, with the hydrostatic axis, is the deviatoric stress. But in practice, when we make a simulation in 2D in particular, we may consider that the pressure, the blue arrows here, is what we apply on the bottom of this rectangle. And the deviatoric stress is the increment of stress on the top. But in practice, this is not fully true because we've got a lot of heterogeneities inside the sample. But most of the time, we consider this. Still, for focusing of typical behavior of granular material, I've seen that Jean Welsh talk about this, and maybe Parang also. Typically, when we shear directly or not directly, when we make this loading, actually we shear the granular, but in a inclined direction. So when we shear a granular material, we generally observe that the shear stress will have a peak at a given displacement or strain if it is dense enough. If the granular material is loose, we will not observe a peak, but whatever the density at the initial state, we will observe a residual shear stress that will be the same. It will not depend on the initial configuration of the granular material. For the volume change, here this is the height change. We'll observe that it will not be constant. And if the material is dense, it will increase. If it is intermediate, it will no, it will densify. It will first become less dense and then densify. And if it is loose, it will go like this. And concerning the yield function of the material, In the space shear stress, normal stress, it will be defined generally by the Coulomb. No, what is the name? The Moore Coulomb criterion. So an affine line. And concerning the flow rule, it will not be associated. It will flow due to friction. It will not be associated. So this page is a kind of a joke, I would say, because I say that the DM is better than anything, because actually with very few ingredients, if we make a DM simulations, we can use simple disks because they are easy to handle. We vary the size. We add some elasticity between the particles. We add the friction between particles. And with only these few ingredients, we are able to model a lot of things. We are able to model the fact that the dependence to density or to the pressure. The volume change can be modeled very accurately, only with these few ingredients. The dependence on the loading history, the stress softening, the complex loading, they emerge naturally to the model. So this is a magic model. This is the better model you can use, actually. You can add complexities, but from this point of view, this is a very good model. But there is actually a price to pay. The most known is the fact that when you make DM simulations, the computation times are very long. We make a simulations and we wait a long time for the result. But there are other things that can bother you. One is the fact that the initial state of your packing is of great importance, and the sample preparation matters a lot, actually. So you can make let's say mistakes if you do not take care about the sample preparation, and also it's long, and the particle shapes also matters a lot. So a few words about the origin of the DM, the Discrete Element Method. This is my story. I don't know if this is the true story, but I consider that the DM comes from the molecular dynamic, where researchers try to model the interactions between atoms at the size of at the scale of atoms by using potentials like that one. This is a picture from Jean-Yves Delaine. And I consider that sometimes researchers call them MD also, but MD is actually for molecules. And the difference between molecular dynamics and DEM is the fact that in DEM, we use unilateral elastic repulsions so that the particles will not overlap. The contact will be, the particle will look like rigid. And also the Coulomb friction between particles. With these two force laws, the molecular dynamics becomes DEM. And this has been done in the early the 18s by Kundal and co-workers. But there are other methods than what I call DM. I can say a few words about them. First, the event-driven methods, where we compute the free flight of each particle. If we know the velocity of a particle at a given time, we know the entire trajectory. So we can compute it. And instead of advancing by constant time increments, we can advance in the simulation event by event. And what we call an event is the collision between a pair of particles. When two particles, when an event happens, so a collision, we can compute the output velocities as a function of the input velocity, and by considering some restitutions coefficients. And actually, in this method, we don't have elasticity between particles. They are rigid particles, and rigid collisions also. No elasticity in the collisions are considered. With this method, it is very fast if you consider a gas, of granular gas. It means that the granular system is very, very loose. If we can model denser packing, but it's not well, how to say, it's not common to do that. Another method is the non-smooth contact dynamics, which is mainly developed in Montpellier, I think. In this method, the particles are rigid. The motion is resolved like in DEM, in classical DEM, but the contacts are treated as non-regular conditions. Instead of saying we've got elasticity between two particles, we will say, for instance, that if we've got a contact, so if we have a small overlap, very small overlap between two particles, so the normal force will be something positive. And if we don't have contact, it will be 0, for instance. We do something similar. We are doing something similar for the friction force. And this results in non-regularity everywhere, in the velocities, in the everything. But this method is less easy, I would say, to handle than classical DEM, because from the mathematical point of view, it is a little hard to model. Okay. Also, we don't have the uniqueness of the solution. It can be something we want to investigate, but not always. If we don't matter about elasticity, we can consider that the particles, the contact are rigid. This is a good method because we can make bigger time step than DEM, and potentially the solutions, the computation can be faster. Okay, one more approach method, the quasi-static method. Actually, I know only one person that would deal with this method. This is Jean-Noël Roux. I don't know if he talked about this, but here the idea compared to non-smooth contact dynamic is to use the elasticity of the contact. So in this method, we consider that we are in a quasi-static condition, and we are able to compute all the force at one time by considering elasticity in the normal and tangential directions. So we will find a solution globally, but because of the friction, we have to consider also that we have also how to say, we have to make projections in two admissible spaces, one which is due to elasticity and the other one to plasticity. So one more time, this method is very difficult to handle, but in some situations we would prefer this method in particular to explore the set of possible solutions in elasticity and also with plasticity. There are another kind of DEM, because some authors in the literature give special name to their method, but actually they are DEM, but with a special feature. For instance, they change a force law, they add cohesion, special cohesion, and they rename DEM by something else. They change the shape of the particles and they rename. So from my point of view, they are DEM. But sometimes in the literature, you will find other names. So what is DEM actually? So as I said, for me, DEM is molecular dynamics, but with frictional contacts, and that's all. So I will explain later in practice how we play with that. But there is a usage of the DEM which is a little different. Sometimes, because the DEM from a computer point of view is easy to handle. Actually, you will see it's easy to program with DEM, and some authors they thought about the DEM to model, for instance, concrete. And with DEM, you can have large strengths easily. You can have cracks, etc. And these authors tried to use force laws in between the particles. Force laws that reflect what they observe macroscopically. And personally, I don't think it's a good practice, because when you model you use distinct elements, rigid elements, a part of the macroscopic response comes from mesoscopic pictures, from the fabric, from the packing actually, and this is lost in the modeling. If you want to use the DEM to do such thing, I would suggest to use instead a method which is done for that. For instance, the lattice element method or the peridynamics, which is made to model continuum and which is able to handle also cracking, crack propagations, etc. So now let's start actually what you are the thing which is of interest. I will try to explain the DEM method and then go to some example of a piece of code. So the starting point is to say that we've got rigid particles, we've got rigid bodies, and we will try to integrate actually the Newton's second law. In a two-dimensional situations, it is written here. You all know mass time acceleration equals the force. And this is actually the first equation. For each particle, we will consider that the mass times, here I noted x, which is the position, but dot dot means this is the second derivative with respect to the time. And this is for particle I. So mass time acceleration of particle I is equal to the sum of the force that act on that particles, which is due to the surrounding particles, G, that act on him. Okay. This is how I'm not the things. And eventually we can add a volume force, here the gravity typically. We make something similar in 2D for the rotation. Here, the inertia times the angular acceleration is the same. We will consider the force that act on the particle by considering the how we name this, the lever branch, okay, plus project the force, and eventually some moment that act on, at the surface of the particle. So the DEM consists basically to consider these equations for each particle and to integrate it. We will integrate in the course of time 2 times, because if we integrate 1 time, we will obtain velocity, and if we integrate the velocity, we will have position. Okay, so basically, it will be an explicit integration scheme to find the position and velocities of all the particles. So to perform this integration, we can use different kind of scheme. Euler, velocity Verlet, which is sometimes called leapfrog, depending on the author, but I'm not sure of that. Maybe there is some difference between the two, but let's say they are similar. The gear predictor corrector that use higher order of instead of stopping at the acceleration, they consider more derivatives. But this kind of integrator use some call them magic number to integrate, and I don't think they are very accurate actually. I've made tests recently; they are not accurate. And the Rouge-Cotta integrator is something which is very accurate, but most of time we don't need to something so accurate. Okay, and with this kind of integration scheme, we need to perform at each time step more than one force evaluation, and this is what costs the most in the DEM. In the DEM. So here, just for learning, let's say, will you explain with the Euler scheme, which is very simple, but in practice we never use that one because it is not stable enough. Actually. So at one time, we've got a position of a particle. If I take this position and I add the velocity, the current velocity of the particle times a small time increment, named dt, I will obtain a new position. And in terms of computer, I will take the current value and change it to that one. So I will make an update of the position. I can do the same for the angular position, the orientation. Okay. And then I do the same, but this time for the velocity. So I adapt the position and then velocity. With this simple scheme, I take the current velocity, I add to it the acceleration time a small time step and put it in as a new value. The same for angular velocity. But to define this acceleration, this is the place where I use the second Newton law. Okay, so I make an integration, but before just after computing the velocity, I need to have an evaluation of the acceleration of the particle, and to do so, I need to compute all the force that act in between the particles, and use the second order, the second Newton law. Second, what is the name? The Newton's second law. Okay. So now let's have a quick look on what we would do with the velocity Verlet scheme or leapfrog. I don't really know what the difference is. So this scheme is very often used in the code. You can find in the you can find in the I would say in the nature, but in the commercial codes, for instance. differently from the earlier scheme, we add the velocity time the time step to update the position, but we account also for the acceleration. Okay, so it's like a Taylor development, but at higher order. And when we will evaluate the velocity of the particle, we'll start with the current velocity. We'll add the current acceleration times dt. But in between the two evaluation of the accelerations, it means that in between these two, we will evaluate the forces between the particles. Yes, we will evaluate the forces. So this will be updated in two stages. We'll first evaluate the with these elements without that one. Then we compute the forces, and then we update with only that one. Okay, this is the particularity of the scheme, and it is known to be very stable, easy to implement, etc. So now I propose to go to some implementations to illustrate what I've said. If you've got questions, it will be maybe after the lecture. So, okay. So, a few words about the system. I use JavaScript to show you the piece of code. JavaScript is something that runs inside the HTML page, like if you were in the internet. Okay, so I need to have an HTML page, and in this page I will call the code, which is in that file. Actually, you don't mind about it. Okay, and the code will be interpreted by the what the name, by Chrome, for example. Okay, so it is easy because I don't need to compile the code. I can use a library which is named p5.js to display things. So with that, it's easy. So to explain the integration, I will first consider a mass point with an initial velocity, so Vx and Vy in 2D, and try to compute the trajectory of this mass point. Okay, to compute this trajectory, I will integrate by using the earlier scheme. Okay, so I don't want to enter deep details about programming, but I think you can understand anyway. I've got here a function which is named run, to which I give the initial velocity here along x and y of the mass point, and I give also a time step. In this function, so the function is there, I will initiate the position of the particle to be 0, 0, x and y, and I will initiate the velocity to be the one I provide. These two instructions is to say that I will display things, and I will display in black with a width which is 1.5. Then I start the integration. I will say why the particle is in the canvas, is in the box, let's say. Okay. I will store the current position. So the x will be prev x. I store x in that variable. Same for that. And I start the integration. First, I will integrate the position by saying that x, I will add to x the velocity times time step. Okay, plus equal means that I take x, which is a memory space, and I add to this space the velocity time step. Same for y. Then I do the same for the velocity, the second integration. If I consider the gravity, I have no gravity, no acceleration in the horizontal direction. So Vx will remain the same, the velocity along x, but the velocity along y will be updated by considering the gravity acceleration. Okay. Then I draw a link between the previous point and the new one. Okay. So this function does this. Then I told you about the library, which is P5GS, that has the particularity to have two special functions. One function is setup. The name is there. It allows us to initiate something. And the second function, which is not here for now, is draw. It corresponds to a time step. We can perform time steps while drawing things at the screen. So here in this example, I will create a canvas to display things. The canvas is 500 pixels by 500 pixels. We clear the background by setting a light gray, okay? And we perform different runs of our simulation, which is defined here. So in each run, the initial velocity is the same, 20 AT, okay? But the time step is smaller and smaller, okay? So what we need to understand here is just the scheme, the LS scheme we use. So to run this, I simply open the HTML file that called the file, the code. It computes things, and here is the result. For the first one, I've got something below. Okay. For the first one, where the time step were big, we've got something which is clearly wrong. And as the time step becomes smaller and smaller, we've got a trajectory that tends to be the same and should be comparable to what we should find if we resolve by hand. Okay. So this is exactly the way we perform the integration in the DEM code. The only thing which is missing is the fact that we don't have force laws here. We only have gravity. So let's have a look on another example where we will have a force law. So before going to the code, I will look at the solution to remember. Okay, we will simply make the integration of the motion of this mass point. This is only a point x and y and the mass, which is linked to the 0, reference with a spring, a linear spring. Okay, so let's have a look on the implementation. So here we still have the function name setup. Remember, it was for P5GS. And then we've got a function named draw. This function will be called periodically. Let's say every time step, this function is called, and we display something on the screen. Before, we've got some global data that I will comment. M is the mass of the mass point. K is the stiffness of the spring. X and Y is the current or initial position of the mass spring. Here is the initial velocity, and this is the acceleration at the beginning, t0. The time step, I set it to something small. I will comment this after. And this is only for display. So at the beginning, I just create my canvas, clear the background, and set a position where the 0, 0, the origin will be. Okay. Then in my periodically called function, I will perform my Euler-scheme for integrating. So as before, I update the position by taking care of the velocity, the current velocity. So here I've got position at time t plus delta t. Then I will make things here and I will comment. And after I will update the velocity. Okay. Just like before. Here I made something different. I say I will compute the distance between the mass point, which is at position x and y, and the origin 0, 0. So this is the distance, and I can define also a unit vector, which is from the origin to the mass point. Okay, done. And then I will use second Newton's law to compute the acceleration. So the acceleration of the intensity of the acceleration is the force, which is due to the spring. Okay, if the spring is there, the force will be 0, and the more the point is far from the origin, the more the force will be, and it will increase linearly. And if I divide this force by the mass, I will obtain the acceleration. So this acceleration will act in the direction from the mass to the origin. So this direction is given by minus ux, uy. And if I multiply this unit vector by the acceleration intensity, I will obtain the acceleration vector, which is here. And I use this acceleration vector to update the velocity. And that's it. This is the first DEM code, not really DEM, that we can do in with a few lines of code. Then I'm drawing things. So I draw the particles with a color. I draw this line. I draw things. Okay. And this code allows us to make this. Okay. Let's continue. I don't have any return from you, so I don't know if you understand everything. But you may have questions. So now we try to see something which is similar, but we will change the force flow. Instead of having a spring, we will consider a kind of gravitational attraction between the sun, which is fixed, and planets. Okay. So here in this example, we've got a mass for my planet. So this is a fake value. I put 1 just for the example. M0 is the mass of the sun, the mass which is fixed, 1 also. And the gravity constant is set to 10,000 here. I don't know why. They are fake values. Okay. Here we've got the kinematic configuration of the planet. So position, velocity, acceleration, the time step, and something to play the planet at the center. So we've got still our zeta function, and then the dual function. So like the previous example, we update the position, we compute the acceleration, I will explain, and then update the velocity. Explicitly, everything is explicit in time. So this time, the only difference is that instead of having a spring as a force, I change the force. So only by changing this line, this small piece of code, I change the kind of interaction between the two elements. Okay, but still I've got one element because the sun is not an element; it is a fixed point So you recognize here the law which is due to gravity, except that the d is not squared. I think this is only a matter of to ease the integration. So let's have a look on the result. Okay, this is the sun, and this is a planet that turns around the sun. It's not very impressive, but the idea is to learn the DEM. You see that the trajectory is not exactly a disk. It's something different. Okay. Third example. Now, to approach what a DEM code is, we will add particles. So we will start with the planet system, with one planet and the sun, and we will add planets. So how could we translate this in the code? I hope you can read. Here I use something which is typical of object programming. I will define a variable which is not a value, which is something that holds several values. And I will say that I can define a grain or a particle, and this grain has a position, x, y, a velocity, and acceleration. It is the way we do in JavaScript. So still we've got the mass for the sun, a gravity constant, but this time, instead of having only one particle, we've got an array of particles. We've got many, okay? In JavaScript, we say that by using square brackets, okay? The time step, something to display, and then the setup. In the setup, we have something new. We don't have one particle now. We have more than one. So in the arrays of particles, which is named grain, we'll push a new grain, which has, it is defined here. The constructor of the grain, you have to define the mass and the position x and y. Okay, so we add in the list of grains a new grain which has the mass 1 and which is at this position. Okay, when this we do that for 4 different grains. Okay, so at the end we've got 4 planets, because grain is planet actually. And when we define the position, actually we define the velocity so that it is tangent to the circle that will define this initial trajectory. Okay, so the Vx depends on the y position with a factor. And then the draw function, theoretically called, is like this. We update the position of each grain. To do so, we loop over the grains by saying that each grain has the index I. So I will go to 0 to the length of the array that all the grains. Okay, we update the positions of the grains by using the velocities, and then we will first compute the interaction of the planet with the sun. Okay, so the distance is the length between the sun and the planet. The sun is placed at 0, 0. Okay, we've got a unit vector. We compute the attraction force. We've got only attraction, no repulsion, and we set the acceleration of the grain. Oh, something is missing. Okay, it's missing, but the mass is 1. We should divide by the mass here. This is a mistake. But actually, we divide by 1. And all the grains are as a unit mass. Okay? So there is a bug here, but it's okay. Okay, this is to update the acceleration due to the presence of the sun, okay, for one particle, index I. Then the particle will be able to interact with the other planets, with the other grains. So we will loop over the other planets with index J, G, J. I say that if J is I will not interact with myself. So continue means I jump this loop, okay? I jump this time, this particle. Okay, this is the branch vector, the distance between the particle, it becomes a unit vector from particle J to I. We compute the attraction force, and we compute the acceleration of the particles. But actually, this acceleration will be added to the current one. At the beginning, we've got only equal, and then we've got minus equal. It means that we take the current value of the acceleration, and we add or subtract the contribution to an interaction with another planet. Okay? And at the end of this loop, which is here, we've got the contribution of all planets and the sun on the particle I. So we use that to update the velocity, and job done. So as a result, we will observe we'll get something like this. Okay. So this time the trajectory is less easy to predict, let's say. We've got a chaotic system, and we see that the planets interact in between them and also with the sun. Sometimes we observe some big overlaps between the disks between the planets and the sun, let's say. But this is due to the fact that we've got only attraction, no repulsion. Okay, so this example is fake, totally fake. The only objective is to explain how the DEM works. Okay, back to the presentation. So we have seen practical example to see how integration works. Now let's go in more details in the definition of force load. So, as I said, we need to compute the accelerations of each particle to define the resultant force and moment. So we need local models to compute these forces. It was the case in my examples. I use a spring model, elastic spring, and also the gravity force law. So I will develop in a few minutes the typical force law that we may use. But first, warning for newbies in DEM. We may think at the beginning that the local force law, the model we define in between the particles, to define the force in between the particles, is similar to what we should observe macroscopically. Okay, so this is a kind of constitutive model of the granular system, but this is wrong, super wrong, because the macroscopic response will be strongly affected by the packing composition and the fabric. In other words, the mesoscale will matter a lot. For instance, you can take a system, remove friction, no friction, okay, you shear, and you will observe macroscopically that you will have in a more Coulomb yield function you will observe that macroscopically you've got a friction. Okay, the envelope will not be flat; it will be a cone. Okay, so this illustrates the fact that when you develop, if in the future you develop a force law, the force law is not directly what you observe at the macroscopic scale. So let's see the force law that we can use. If we consider that we've got elastic particles, they will be rigid particles, but we will consider that the contacts are elastic. And to do so, the common law that is often used is the Hertzian contact. In this law, some assumptions have been made. So we make assumptions on the shape of the particle. For instance, we can say they are disks, but they are perfectly smooth. The particles are elastic. And so there are some assumptions like this. And with these assumptions, it is possible to derive what the force will be. And generally, we find that the elastic normal force, so E means elastic and normal force, of particle G acting on particle I, is something that depends on the elastic properties of the two particles and on the radii of the particles. And it will be, it will evolve like this is the deflection of the particle at the power 3/2 for disks. What I call deflection is because the particle will look something like this with a lot of exaggeration. But in the DEM code, they are rigid particles that remain perfect circles. So the overlap between the particles can be said as a distance which is negative, and minus this negative distance is called what is said to be the deflection of the particle. Okay, so as you see that with this model, the force law does not evolve linearly with the deflection. So this is a non-linear power law model. And we use it when the elasticity of contact is of primary importance. For instance, if you want to study wave propagation, elastic wave propagation to granular packing, this is a good idea to start with such a law, because maybe the elastic one will be not enough. Okay. Most often we use elastic relation, just like I did with my example. And the way to write the law is to say that the elastic normal force is the deflection times a stiffness coefficient, okay, Newton per meter, if the particle overlaps, if they touch. If not, the force is 0. Okay, this is the simple law of the life, let's say. When I should use this kind of law, if I'm able to consider that linear relation is enough. For instance, if we've got a Hertz contact, but the deflection is so small that we can consider that the relation is linear, we can use instead this law because the computation will be faster. But most of time when we model, it depends on the application, but when we model geomaterial or granular packing, which is dense, most of the time we don't mind about elasticity. Okay, if you remember the typical force law we've got here, typical mechanical response, maybe you have in mind the behavior of metal, where we've got an elastic part and then something which is like this. with softening or not. But with metals, this part is an elastic part. With granular materials, most of the time, this part is not elastic. If you unload, it will go nearly vertically, okay? And elasticity corresponds to a very small part of the curve. So actually, depending on what we are doing, we don't mind about elasticity. It is not always the case, but often the case. I'm sure some people will not be happy with me saying that. But practically, when we use such a law, we do not observe in most applications difference with the Hertzian model. Okay. So in this case, it's better to use this law. Okay. Sometimes we add to the normal component of the force a viscous term, dashpot, a damper, let's say, that writes like this. So the normal force, the viscous normal force is dn dot is the relative velocity between the particles times a coefficient. So there will be a velocity dependence on the force in the normal direction. But if the contact do not touch, this viscous term is zero. Okay, when to use this kind of law contribution? When it is physically sound. If you've got particles that are viscous and the loading which is fast enough to have something, you have to add this term, this kind of term in the force law. But sometimes we only need to dissipate energy. So we may also use this viscous term as a way to dissipate energy for a numerical reason. Okay. So it depends. There is not a single rule. It is like a recipe. When you make them, it is like a recipe. You have to adapt to the situation you play with. Coulomb friction. Okay, when you play with grains at the size of sand, for example, you need Coulomb friction every time. So how to write this? First thing, we cannot, Coulomb friction is like a perfect plastic law. So we will have a tangential force that will be oriented in the opposite direction to the sliding direction. If we've got two particles that are contact in friction, and at the given threshold, which is proportional to the normal force, the tangential force will not evolve anymore. It will be stuck to this limit. But if the normal force change, it can be changed. It can change also. Okay. So the way to write such law is a little different. Instead of writing directly what the force is, we will compute the increment of force, and we'll update the force at each time step. So the tangential force will be the sum of all these terms for all the time. Okay. So to account for the Coulomb cone, I suppose you know about this. We can define it with an angle of friction, and we can define a coefficient which is tangent of this angle. So generally we use that coefficient. It means that if you want the tangential force cannot be more than something which depends on the normal force. Okay, so if we are here, the tangential force cannot be more than this. If we are here, I hope you see my arrow, the tangential force cannot be more than this. Okay, friction, Coulomb friction coefficient. So we will say that the tangential force will be elastic as long as the tangential force is less than mu Fn. Fn elastic. Okay. So this is the condition. And here we will say that since this is an increment, we will use a stiffness that will create an elastic force in the opposite direction to the velocity. Okay. So this term is an increment of displacement due to the current velocity. And this term is a unit vector in the velocity direction. Okay. So if we lose contact, the entire force is removed. Okay, this is some explanation. This is a law which is hard to implement the first time. But actually, there is something with this law. It is wrong. It is actually wrong for many reasons. The first reason is that it is not objective. It is not an objective law. It depends on the observator. And okay, because if we got a flat surface and a flat body that slide, it's okay. But when you've got particles with let's say sphere shapes, the contact position and the sliding directions may change during the loading. Okay, so there is a problem. But in practice, I don't know any DEM code that use something different, a lot different. So this is wrong, but in practice, it is used by everybody. And up to now, I have no proof that we should use something else. Okay. So maybe I will show also at the end, depends on time, how to implement such a law. And I've just seen that I'm low. I should go faster. So now a few words about the dissipation in DEM computation. Why do we need to dissipate energy? Because a DEM computation is by essence a dynamic computation. Even if you are simulate a quasi-static situation, the model is dynamic. Okay, and it is very difficult to stabilize this system. You can if you use very small time step, but at a given point you will be obliged to dissipate energy. So if you do nothing, you will dissipate thanks to the viscosity at contact if you use it, and also to the friction, because you've got an hysteresis in the curve. So you will be able to dissipate, but sometimes you need to dissipate more. In particular, if you want to obtain a static condition, well balanced, you will have the possibility to use a damping solution, which is named Kundal global damping. This solution is not physical. It acts by weighting each acceleration, which is opposite to the velocity, component by component. So this is something which is like a parachute. It's okay to obtain a static situation, but it is not physical. You add a parachute to each particle. So be careful about this. It is implemented in any any code you will find in the market, let's say. So warning, global Kundal damping is to be used only to reach a static balance, a well-balanced static condition. If you are doing something which is dynamic, avoid to use that, because it will increase the resistance. Okay. you've got another solution. You've got many solutions. Another solution is to use a global viscosity. It is like the particles are sinking into a viscous fluid. Okay, so you in the resultant term, in resultant force on the particle, you will add a term which is due to viscosity. Okay, so you can do that because physically it is what you've got. Okay, you are allowed to make what you want if you have a liquid around your particles. You may model this like this, but you may also use this to damp the system numerically. So there are two examples. There are many others. Okay, now when we will perform DEM computations, we will need to set some parameters. One parameter which is of importance is the time step. So to define a criterion to define what a good time step is, we rely on the ODE, ordinary differential equation, that correspond to a mass with a spring, only a mass and a spring. So it writes like this. So here m is the mass. This is the second derivative of the gap, of the distance. So the acceleration, and here the position, stiffness. If I solve this equation by hand, the solution will be periodic. So with an amplitude and a frequency. Okay. And to obtain, if we consider a collision of two particles with this wave, the wave will be like this. So a collision will correspond to half a period. So we can define here that half a period is pi times the square root of the mass over the stiffness. Okay, so very often the critical step is defined like this. Some authors say 2 pi. I don't know why. My definition is that one. You may find other definition, but it will be okay. You will see. We may also consider that we've got a dashpot. We don't have only a spring with the mass, but also a dashpot that will damp with velocity. In this case, the critical step, the critical time step will be that formula. We can find it by hand, but actually this term is something which is small. But in practice, this time step will always be larger than that one. So to define the critical time step, it's better to not consider that contribution. Okay. So in practice, to define now the time step, we'll say that the time step has to be a portion of the critical time step. There is no well-written rule. This is only a recipe. By experience, I personally found that we should use a time step which is at least 50 times less than the critical one. Okay. Some authors will use 20. Some authors will use 100. Maybe, I don't know, actually. You have to experiment. But often, if you are newbie in the DEM, you will, in your first simulations, you will observe some blasting, some explosions. Often, this is due to that. The time step is not well set. Okay, I will make a demonstration. So in practice, instead of having where it is m over kn, we will take the smallest m and the biggest stiffness, so that the time step is the smallest possible. And instead of taking the minimum mass, we take actually the minimum effective mass, because each spring corresponds to a pair of particles. So we define an effective mass like this, and here is the formula. This way of finding the time step is the way that will find the smallest time step every time. You may also consider the velocity of elastic wave propagation to the packing, but if you use that criterion, the time step will be bigger. So that one is the one which is most often used due to that. Okay, now we need also to set the viscous parameter, which is used if you use viscosity here. If you use this kind of law, you've got a viscous force in the normal direction. You will need to set the viscous parameter. So to do so, we consider the ODE with a damper, and we consider that we should have an amortized, a damped sign as a solution to be correct. If not, the particle will never go back from, it will be stuck. So it is not physically possible. So if we consider that, it means that we need a complex solution, and this has to be less than 0. Okay, if we write the characteristic equation, this has to be, the discriminant has to be less than 0. It results that the critical has to be 2 times square root of m times stiffness. Okay. In practice, to define something which is physically sound in our simulation, we will instead define the user will enter a value which is alpha, and that defines a portion of the critical viscosity. That way, we are assured to define something which is physically sound. And this portion has to be, it can be 0, it means you don't have viscosity, but it cannot be 1. It is in between 0 and 1, but you will not be able to use 1, because if not, the solution is not okay. What time? Maybe I continue a little, and then I will go to a piece of code which is a little bigger. So when we make DEM simulations, we need what I call good practices. And to practice these good practices, we need to rely on these dimensionless numbers. I'm pretty sure that Jean-Noël told you things about this stiffness level, kappa. So here is a definition of the stiffness level of the particles. Why don't we use only Kn? Because physically, we want that the deflection of the particles are small compared to the particle size. Okay, so if the pressure we apply on the sample is high, the stiffness has, how to say, the stiffness has to be compared to the pressure applied on the sample, because the overlaps between the particles can be big because due to the big pressure, but it can be big also due to a low stiffness. So this is how is derived this relation, this number. Okay, so you see here the stiffness you will use in the simulation, the pressure that will be applied on the sample, the mean diameter, which is noted like this, and here we've got the power that use a capital D. Capital D is the dimension of the system. So in particular, this stiffness level in 2 dimensions will be only defined by stiffness over P, because this term will be 1. Okay. In 3D, this term will be D. mean D, mean diameter. So in practice, we know we can assess the order of magnitude of kappa in experiments by relying on the pressure and on the Young modulus. And let's say in practice, we will have small overlaps if kappa is more than 1,000. Less than 1,000 is it needs to be justified physically. Okay. Here, instead of defining alpha, we just have seen alpha, which is the portion to define the portion of the critical damping coefficient. As a user, you may, instead of defining alpha, you may prefer to define the restitution, the velocity restitution between two particles. So the velocity you have, the reflected velocity compared to the input velocity, it defines something which is physically that has a physical sense. Okay, so there exists a relation between these two variables that can be used. Inertial number, I think Jean-Noël told also, for those that have seen the talk of Jean-Noël and Farang, they told about the inertial number. This is a common number used by the community of physics that works on granular materials. And how to say, this value, I, will say you in which regime you are. Are you in a static regime, a quasi-static regime? Are you flowing like a fluid? Or are you a gas? Okay. If you are performing a quasi-static regime, you have to be careful about the value of E, of I in English, the inertial number. Okay. So one definition of this number is the strain rate times mass, pressure, mean diameter. Okay. So if you want, for instance, to make a biaxial compression in the quasi-static regime, you will find the I which is okay for you. You have to rely on what the community says about this. Okay, maybe 10 to the power minus 3 is okay for a simulation. It's not the case in experiments, but for a simulation, 10 to the power minus 3 or minus 2 maybe is the limit, the fastest loading you may use. And using the relation, you will impose I and you will define the strain rate. So you will be able to define the velocity you need to apply on the biaxial for the biaxial compression. So one other parameter is the friction coefficient, which is already a dimensionless number. Okay, I will have a few times for the code. Maybe a few words about some data of interest that are often used when we are analyzing DEM simulations. The first one is the coordination number. It means this is the mean number of contact that each particle has. So, but the definition, it is often noted Z. Since one contact acts between two particles, it is two number of contacts divided by the number of particles. In the situation where we don't have gravity, or yes, the packing will be strange because we will observe some particle that float, that have only one contact. Okay, and this is due to the fact we don't have gravity. So sometimes these particles are named rattlers, and we may have another definition of the connectivity that accounts for the presence of rattlers. that they avoid the rattlers. Okay, so we may also use that. Okay, here just a small words about the solid fraction, which is often used. This is simply the volume of solid, the sum of the volume of all particles divided by total volume. And this variable is often used actually in the granular papers, most often than the void ratio or things like this. Sometimes it is called density, but this is misleading. I prefer to call it solid fraction. So I will try to show you the DEM code, which is small, but I hope you will understand things. So here is the code. It is little longer, as you see. But anyway, this may appear as something long, but actually there's nothing in the code. So here I define what a grain is. This time I've got kinematic parameters, the resultant force. This is not good. And okay. I didn't talk about the neighbor list. A few words. If you make a simulation with a DEM simulation, you will have to compute force between each particle. So if you will have to have, if you have n particles, the number of contact interaction you will have to compute is n at the power 2. Okay, so it's big, and you have to do that every time step. And if you do nothing, you have many particles, the computation will be too long, really too long. So one solution is to manage a list of neighbors, a list of particles that are close, that may interact, and to update this neighbor list so that the number of contacts, the number of interactions you will have to compute in the code will be a lot less. Okay, so in this version of code, I've got a list of neighbors. A neighbor is something that holds the number of the two particles that interact, something that say if they touch or not. It is for post-processing things, and the normal and tangential force of the link if they touch, obviously. So here I've got an array of grains in this example. These two variables is because I will put the particles on the grid at the beginning. They will be on the grid. There is 4 walls as a box. Maybe I should show the simulation. So the code I will comment is that one. Okay. Particles are on the grid. Here in this example, the gray level is the velocity of the particles. I've displayed the normal force as a branch for which the width is proportional to the normal force. This wall and this wall, the bottom and left walls are fixed. And at the beginning of this simulation, I apply a pressure on the top wall and on the side wall. Okay. Okay, for now I will stop. So at the beginning, I've got this number of particles vertically and that one horizontally. These are the radii of the particles, minimum and maximum, and it is homogeneous in between the two. The density in kilogram per volume is that one. It corresponds to the density to soil particles. Sky is for display things. X max is the position of the right wall. Y max is the position of the top wall. That one will be the position to compute the strain. And here a velocity to add an agitation at the beginning. I have not a lot of time, so I will try to concentrate. Okay, here we see that instead of defining directly the stiffness between the particles, okay, I will instead define the dimensionless number kappa to the minimum value, because with small value of kappa, the simulation will be easier, okay, to run. I will look on the chat. I will check after. Okay. Here, viscous rate is set directly, and I define an inertial number. So actually, in this simulation, I will perform 4,000 steps with hydrostatic compression. So pressure and pressure on top, pressure on side. Okay. Then the pressure will be maintained on the side, but on the top, I will apply a velocity. Instead of defining a velocity, I prefer to define an inertial number, which is that one. This is faster, okay? Okay, and the actual velocity will be defined as a function of the inertial number, okay? Instead of setting a value here, I prefer to give it this value, which is dimensionless, okay? This is a good practice. Now, there's no equation. I didn't talk about equation. The time step. If you remember, the critical time step is that one. I computed before the mean mass in the sample. I've got the stiffness. So here's the equation. Here I consider that if I divide the time step by 20, it will be okay. Okay. So maybe we may have a look on the simulation. No, not one. On the simulation. So here, what happens if I apply the pressure here with a time step, which is the critical time step divided by 20. Let's have a look. Have a trial. Have a try. If I divide it by 2, okay, what will happen? I reload. But it works. Super robust. One. This version is too robust. It still works. My demonstration is failed. Okay. Let's be extreme. I do not understand why. Here the time step is bigger than the critical time step, and it's still working. Maybe not at the end. Okay, let's continue.
Meanwhile, Vincent, you have not much time. Can you just tell what are you plotting here? What are you plotting?
Okay, so I will not be able to comment all the things. I just want to say that it's as you may see that it's easy to make a code, okay, with a few lines. My goal was to explain, but okay. What is plot here on the bottom is the coordination number. We see that during the compression, it increases, normal, okay. It oscillates also. On the top, we've got the solid fraction. So it increases. and at the given, here my time step is too low. I will go back. At the moment, you will observe the stabilization of the coordination number and also to the solid fraction. Okay. And okay. So the applied pressure is 1 on this side and this side. And we measure it here. So now we don't have a dense cracking yet. So it oscillates. But at a given time, it will be nearly 1. Okay? Because we apply, something happened here, which is fine. Okay. We've got the coordination number here, the time step. And when the step number will be 4,000, we'll go to biaxial compression by imposing velocity here. So the axial strain will increase. Okay. But before, here we are coming to the something which is nearly stable. It will be more stable. Actually, if you make a computation with a normal code, let's say, it will be faster. Yeah, it is slow because I use something which is not developed for that. This is not. This is an HTML page, you know. Okay, here we see that first we observe the force chains. I'm pretty sure that Parang told about the force chains in this talk. We observe that the solid fraction tends to be something fixed, and the same for the coordination number. Yeah, the value is very low because there are a lot of what I called rattlers. Okay, and if we wait a little bit more at time 4,000, the axial strain will start to increase, but the curve will not be nice because we've got few particles, and also we are in a situation which is strange, which is weird, because the particles are not allowed to rotate here. So the response is strange for those who know the typical curves. So we may write a little to see what happened, and maybe I can stop if you wish and go to question.
So should we start the questions?
Yes, if you want, but if you wait a little, we are
a bit more
close to see the up. It starts. Okay, compression starts. The force chains change. They are more oriented like this. Okay, the axial strain increases, but actually the solid fraction or the coordination number does not change a lot. So when I prepare this simulation, it looks strange for me. It looks weird. Decrease.
It is not.
So here we may see a correlation between the solid fraction and the coordination number, but actually there's no correlation. Jean-Noël Roux is able to build the samples where he controls the coordination number and the solid fraction independent, quasi-independent. So I can stop.
Okay, you're done. Thank you. Thank you, Vincent. We have 10, 11 questions. So you have to provide short answers if possible for you. Okay, so let me start with, Pritom Sarma, who has a question, more of a general question here. Can the bonded particle model type of DEM popularized by Potiondi and Kundal be used to model general consolidated rock fracturing processes and seismicity?
they are often used in the literature, actually. What we call bonded particles, I think they are elastic bonded in the normal and tangential direction, and they are often used, actually. You may find a lot of papers dealing with that.
So what is your suggestion about this model? Do you think it is a good model?
It is, but any model is a good model. But at one point, I thought that you have to be careful. Maybe you should use LEM or perodynamics, but it is not the case. This is a good model, actually, but you have to be aware of what you are doing.
Yes. Okay.
You are not making a granular material. You are using DEM to model a continuum. So you keep it in mind, and it's okay. You can use DEM to do that. There's nothing forbidden.
Yes, I remember Kundal presented this model a number of years ago in Oswa during the alert workshop. And it was to some extent, I mean, he showed that it is working for fracture and so on.
It works.
Yeah, it works very well. Next question by Denis Dumont. Which language would you recommend to write his own DEM code? Is there a more appropriate language in terms of time calculation, quickness, or ease to write?
No, it's a matter of test. You have to use the language. You have to use a language which is compiled. So don't use Python. Don't use JavaScript as I did. Use something like C, C++, Fortran if you want. I personally like to use C++. I may recommend to use C++, but Fortran is okay also. Don't use the interpreted language.
Like MATLAB.
MATLAB is not a good idea. For prototyping, it's okay, but for making simulation, it is not. You will never be able to hold a high number of particles.
Okay, a question by Yiqiu Zhao. You mentioned that in simulation, I, inertial number equal to 10 power minus 3 is considered quasi-static, but this may not be the case in experiments. Why this value may be not considered quasi-static in experiments?
No, in experiments, they are not, because we make experiments by changing the inertial number. And we find that the transition may be for lower values. I don't know, actually, maybe 10 at the power minus 5. Sometimes we make experiments with I equals 10 at the power minus 9. Okay. Yes. But when we make DEM simulations, it's very difficult to reach this value. So we are somehow obliged to use bigger values. If not, the simulation will be endless. So there are values that are accepted by specialists. They say 10 at the power minus 3 is okay. But that's all. You have to check that there's no dependence on velocity.
And also in experiments, the time step is easier to change now.
Than what?
In experiments.
Yes. You have to, yes.
Okay. So Badr has a question. Is this method, so I assume it's DEM, applicable to coupling problems, thermomechanical, hydrothermomechanical, and so on?
Yes, of course. You can use it to couple methods. For instance, you can model the fluid that surround the particles with volume, finite volume, lattice Boltzmann, what you want. So this is done in the literature. You can also couple DEM with FEM by making a side-to-side climatic coupling. Okay. You can also consider coupling as a multi-scale simulation. Like you can couple FEM with DEM by making FEM, and instead of having a constitutive law at each ghost point, you may have a simulation. I'm not sure I'm completely answer the question, but of course you can coupling and you should, because the granular materials are not always dry granular materials. They are actually more complex. So that depending on what you are studying, you will need to couple for sure.
Okay, good. Next question by Yushen Zhao. Do we need to worry about the critical increment time dt, time step, or maybe the critical value of the time step for particle rotation equation, or the critical dt for particle translation equation is enough for determining the time step?
Actually, I don't know. I don't know. By experiments, the critical step are provided is enough. You may try to define one with the rotation, but I'm pretty sure, but not certain, that it will be bigger.
Bigger with translations, you mean?
No, with rotation.
With rotations.
I'm not sure. I'm not sure. But in practice, this is the one which is used. So sometimes they mix the criterion and they take the smaller.
Okay. Auxi Zhang, hello. I have a question in terms of stiffness level. From what you show, the stiffness is related to the pressure. My question is, if we carry out simulations on a DEM sample under different pressures, do we need to use different stiffness parameters under different pressures? Thanks.
Yeah. This question is difficult, actually. With DEM, we always have receipts. Okay, so we will try to define what is the biggest pressure of the system we are simulating, to define this, and we will define it only at the beginning.
Yeah.
This is not, because if you play with that, it means that you will change the stiffness or during computation. But the physical stiffness is Kn. This is not the kappa.
So it means that you consider, as far as you are not interested in the elastic behavior, such as the relation between stress and strain, then you can change Kn, because basically you assume that this is just for the calculation of forces. This is just an intermediate variable used to calculate forces. But as far as it is small compared to the large compared to the applied pressure, it doesn't matter. It can be changed.
Yeah, it's only a matter of order of magnitude. Yeah. You have to know if your kappa is 1,000 or 10. Okay.
So it can
or
be
1 million. Huh?
Yeah, it can be changed.
Yes.
It can be changed. Yes. For example, when you fill a box, during filling, the stiffness can be high, small, because you have only the weight of the particles. But when you apply a confining pressure, which is high, then you have to increase also this.
Kappa will change during the simulation if you fill a box, for example. But it is not the way it is used. Actually, kappa is here only to define an order of magnitude to set your stiffness. Yeah. And you are in charge of defining what is the pressure to be considered to define the kappa to be used to define the stiffness pressure, the stiffness friction.
A question by, yeah, please. Okay, a question by Luisa Orozco. Hello, thanks, Vincent. I have some questions for you and Farhang. Okay, how can we consider the rolling resistance? Are there different approaches depending on particle shape or other particle properties? How does one choose the value of mu r? the coefficient of rolling friction.
She knows the answer partly. Okay, actually, it is defined similarly to the Coulomb friction. Okay, but for rotation, you may consider it with viscosity or with elasticity, but you don't have to this is not the same thing as the resistance, the moment resistance, which is due to the fact that the particle is not a sphere. If you've got two contacts, it is something physically different to a moment. I'm not sure to answer the question.
I think that's the question is that whether what are the criteria for choosing the value if we want to use this?
You have to rely on a paper written by Farron.
Yeah, I don't know. Actually, it is a vast question, and the question is that you didn't introduce it in your course. So for people who are listening to this course, one should first explain what it is. So because it is not explained, so it's hard to discuss it here.
You want me to explain or?
Yes.
Okay.
Would be good.
The rolling resistance is, you may have between two particles when the rotation change, the relative rotation between two particles change, you may have a resistance which is a moment resistance at the contact point. And this behaves just like the friction. At the beginning, it is elastic, linear, and we've got a threshold that depends also on the normal force, from which the moment will be constant.
Yes.
And this is sometimes used to mimicry the fact that the particles are not disks or spheres.
So it is the work by Nicolas Estrada and collaborators who showed that in a very detailed manner that we can use the rolling friction as a measure of the angularity of the particles, because we know that angular particles, not for the same, with the same mechanism, I mean, it's not a moment, but the angular particles, because of face-face contacts between particles, also can transmit a moment. So,
but
we can use it.
You are sure that this is the case, whatever the shape of the particle? Because they were regular here.
Well, no? There is a one-to-one, there is a one-to-one correspondence between the several parameters, like the shear strength, and the packing fraction. So we can know for which value of mu r. So I really recommend this paper to people who want to use this. It is, I think it was published in 2012, Nicolas Estrada, and it shows that for a given value of mu r, you have an angularity corresponding to that value. And if you use that value, then you get exactly the same value of the shear stress. So it's quite detailed. So it's good way.
The open question is it still okay, valid, if for example the particles are elongated?
Yes.
Maybe the one-to-one correspondence will not be.
Yeah, sure.
Open question.
Yes, I like your course, Vincent, because you are questioning everything. It's that's great, because often we have to learn. Most people learn enough to know that they know, but we have to learn even more to get the question what we know. So let's. We have still questions. Standa has a question. I would be interested in methods for applying normal stress N in DEM. Sometimes N is maintained at a fixed value by adjusting volume. Similarly to barostats used in MD. Sometimes external force is applied so that stress oscillates around the desired value of N. Do you have experience with use of different methods for applying normal stress?
Actually, I did not fully understand the question. I understand only the end. To apply on the boundary force, you may consider that this boundary as a mass, and you will treat it as a particle, okay, with a mass. The difficult thing is to define this mass, okay. And then you add the force in one direction, and you perform the integration just like a particle.
I think the question is about, well, you may apply the value of the force on the boundary, but you may also apply a servo-controlled system. That's what you have done, I think.
You may have no servo. You can apply the force and it will work. Then you will have, you can also add the servo that as a function of the current force that act on the wall, update the force that you apply, or update the displacement, the velocity with a servo. It's less easy to do, but sometimes it may be useful if you want to control finally the stress.
Okay, so the idea is to be able to apply a velocity on the boundary instead of a force.
Yes.
So you apply a velocity, but you get a force on the average, which is stiffness.
You update this velocity as a function of the force that you measure.
Yeah.
The force of the other particle that act on the wall.
Yeah.
Okay. Maybe Luc. No. Luc made a paper on that. Luc, I don't remember the name.
Yes. Okay, but we know that.
I may send paper if you want.
Okay, this is a good way of avoiding strong fluctuations, I think, in general. For example, in contact dynamics, boundary conditions with elastic springs would be very useful. Okay, Yiqiu Zhao, another question here. Is there any guide rule to choose a proper tangential spring constant KT? How would changing KT over Kn affect the global mechanical properties of the sample? Many thanks.
Generally, KT is the KT over Kn or Kn over KT control the quotient ratio only in the elastic domain. Okay, so this is the way KT should be set. So if we matter about elasticity, okay, KT over Kn or inverse control the quotient ratio. Okay, most of time we choose KT equals Kn, but still this is a recipe.
Okay.
Okay.
Some people use 0.8.
But, why?
Okay, so it is a question of the choice of the Poisson coefficient, but that's the same question whether you use Hertz or you use a linear spring, how much it makes difference. So it's the same for the Poisson's coefficient. It can be changed, but sometimes it's not significant for the problem that we study. So
typically, if you model a concrete with cohesive bonds, the elasticity will matter a lot. So the question may appear in this case, but if you are dealing with a granular material which is not cohesive, like liquid, I think this is not a question. You can choose 0.8 or 1, it will be okay.
Yes. Or it can be important for volume controlled flows.
Ah,
So when the volume is fixed and you have high packing fraction, solid fraction, then it can be important for,
okay.
I assume. Yeah, so there are a lot of actually open questions or questions that are important for. So we have a question by Peyman Khadivin Pano. What is the difference between the DEM, DEM, and FEM physically?
Physically? Okay. FEM needs constitutive laws. So you have to average the behavior in the law that you give to FEM. Okay. This law may account for different features. For instance, volume changes. You have to set it in the law. If you want to make a cycling loading extra, it has to be defined in the law. Okay, everything you have to analyze has to be defined in the constitutive law. With DEM, the approach is different. You define what is the interaction between the elements and all the other features. They appear naturally at the macroscopic scale. So this is the difference. With DEM, you pay the price by having long simulations, etc. But if you put the good ingredients in the simulations, you will observe very complex things at the macroscopic scale. But with FEM, you will observe only what you put in the model.
Okay, so in the DEM, the physical input information is input at the particle scale.
Yes.
But in FEM, it is at the macroscopic scale. So it's okay.
But the DEM will account for the mesoscopic scale naturally.
Naturally, yes.
So this is a big difference.
Yes. Romain de Lubins, are there any extensions of DEM without the rigid body assumptions? For example, to account for thermal expansion of particles or chemical strain induced by intercalation of chemical species inside particles.
I did not follow. Can you repeat the beginning?
Are there any extensions of DEM without the rigid body assumptions?
Without? Maybe you think that there are some DEM modeling where we can change, for instance, the size of the particle.
Size, yes, expansion, or chemical strain. For example, particles that change a lot, their shape, for example.
Okay.
Can be.
You can do that. When we make a rigid assumption, it's for the model is written like this. But even if you've got a rigid assumption, you can change the shape. Maybe you can rely on what Jean-Yves Delaine did.
Yes.
During I don't know, during his thesis or no. But for instance, he considered the solid bonded particles that model the wood, for instance, and he considered that due to humidity, the wood will what the word?
You would have an expansion,
Yes.
change of size of the particles.
Yes. So this is doable.
Yes.
You have to assume your hypothesis, and it's okay.
It's okay, but or you can couple DEM with MPM, for example, for particle shape change.
Yes, Saed,
for example, has done this. We have to go faster because at the beginning we had 10 questions. We still have 10 questions left.
Okay.
Okay, Duadi Saidan is asking this question. What is the order of magnitude of the intergranular cohesion force for the case of cohesion by capillarity?
With capillarity, this force depends only on the nature of the liquid and the interfaces. So it will depend on the angle of contact of the liquid on the particles and the surface tension, things like this, and it will not depend on the particle size.
Mm.
So typically for water, and let's say millimeter for water, it's a 10 at the power -4, if I remember well, newtons. In case of another equation, you can define a dimensionless number to tune your equation.
Okay, it's basically the interface. I mean the surface tension of water vapor multiplied by R, the reduced size. No, the force.
Well, yes, not reduced, the geometric mean.
The geometric mean. Yes, geometric. Okay, dear Vincent, question from Gustavo Martins. Dear Vincent, can you show an example of DEM code in 3D? Do you have some reference to show us? Well, we don't have time to show that.
No, for sure.
Okay, so that's clear, but I don't know.
Soon there will be a paper on the code name Rockable, which is 3D with spheropolyhedron.
Okay, maybe we can send this document to everyone.
It is not yet fully written.
Ah, okay. It is not complete, you mean?
Yes.
Okay. So it can be during this course, if you have any document, we can distribute it.
If a
preprint or something.
I can have a look. You can also refer to the YED.
Yes.
The code developed here in Grenoble. I don't work with this code, but there is a lot of documentation concerning the code himself and the physics inside.
Okay, so maybe you can provide in a few lines or on one page, let's say, where people can find this code, or adding a reference to, I mean, a link to this document that you were talking about.
I can do that.
We send it to everyone.
Okay.
Clearly, because this course is really a condensed course, which would require 10 hours condensed to 1 hour and a half. So it's difficult, of course, but that would be good to send some document to complement the course.
Okay.
You have. Okay.
Yeah. You will have to remind me.
Yes. So maybe one of the last questions here, because people are leaving now. We are already 8 minutes over the. Okay. Last question. Maybe Niels Audrey. Hello. In addition to the force of repulsion between particles, is it possible to add an attractive force corresponding to adhesion? What relation to use between the adhesion force and the distance? Thank you for your presentation.
Oh, there are many. The easiest one is to do like this. If you see my screen, I've got the equation force here, and in the force law, we can simply add this term to the normal force. Okay. Another solution is to use here. Okay. So I cannot find. First solution, add a negative term to the normal force, okay, when the particles touch one another. Then, depending on what you are modeling, maybe this equation may be due to energy surface energy. It may be due to capillarity, etc. And in this case, you have to find the literature or develop your own cohesive law, which is nothing else than a negative force add to the normal component of force. That's it.
Right.
I may suggest a number, but it depends on the physics you are playing with.
Okay, thank you, Vincent. I think we stop here. So we have